Hello. If you like the content that I produce, then please press the subscribe button now. Limits are extremely important in mathematics, and especially for understanding calculus. Previously, I discussed quantifiers and how mathematical notions can be expressed in precise terms. To better understand limits, I'll employ an informal definition as well as a formal definition. The informal definition is, effectively, that the value of a function f of x tends to some limit b as x approaches a. Limits can be multivariate, although for this presentation let's focus on single variable functions and their associated limits. The formal definition can be referred to as the Weierstrass epsilon delta definition and is more complex. However, I will leave that for later. The formal definition is sometimes referred to as the Cauchy definition too. The first concepts to discuss would be the left limit, the right limit, and the existence of a limit. The left limit is almost exactly as you might expect. It would be the value of a function f of x as x approaches a from the left side, or as x becomes increasingly positive from the left side of a. The same idea applies to the right limit. The reason that these are so significant as different concepts is that sometimes these limits are not the same. Functions can have complex behavior, and it is possible that the left limit and the right limit mean different things. The notation for each limit and the direction they come from are shown visually here. A simple example involves f of x equals 1 over x. From the left side, the limit as x approaches 0 from the left of 1 over x is equal to negative infinity, and from the right side, the limit as x approaches 0 from the positive side of 1 over x is equal to positive infinity. Since the limits from each side are not equal, not only is there not a limit at x equals 0 for this graph, but this also represents a discontinuity in the graph. To have a limit exist, it must follow that the left limit is equal to the right limit for some value L. An example for which this holds is for f of x equals x squared, where the limit as x approaches 0 from the positive side of x over x squared is equal to 0, which is also equal to the limit as x approaches 0 from the left side of x squared. And so the limit is equal to 0 and it exists. I'd already shown an example for which the limit is infinite, and I hope that it is intuitive enough to grasp. The infinite value indicates that the function is growing without bound at that point in the graph. When a graph has such a limit, it is often referred to as a vertical asymptote. There are sometimes also horizontal asymptotes, which arise when considering infinite limits or when x approaches positive or negative infinity. For example, the limit as x approaches infinity of 1 over x is equal to 0, and the limit as x approaches negative infinity of 1 over x is also equal to 0. That is to say, f of x equals 1 over x has a vertical asymptote at x equals 0, and f of x equals 1 over x has a horizontal asymptote at y equals 0. There are sometimes also linear asymptotes, however that is not as common. In the next video, I'll cover the formal Weierstrass epsilon delta definition, the limit laws, the squeeze theorem, and some special limits that are critical in calculus. Thanks for watching, and see you in the next video.